Hello and welcome to Intro FBD. This is going to be a practice through what was test 1 in 2019. So 2020 we don't have tests. It's going to be a different format where you take a practice problem like the style that was on past tests in this problem set 1 solutions file, and then transform it into a version of a new solution to a problem that you came up with, which is kind of in this style. But this gives you an idea of the benchmark for difficulty. This is on the easier side of the problems in this problem set file. So strive to go for this difficult or more difficult if you can. It kind of scales from this one all the way up to the block in a turnpike problem, which is on the scale of the hardest things that you should be able to solve for this topic. If you can do even harder problems, then that's just incredible. Go for it. Okay. A 5 kilogram block starts from rest on a horizontal surface at location x is 0 when it's acted on by an external force in the positive x direction, given by this, where t is in seconds. The surface has kinetic friction with coefficient of 0.3. Draw a free body diagram for the block is the first task. Okay, so let's get our paint.net here. I'm going to hit O to select the line tool, and then hold shift and right click across to draw the horizontal surface. Now if I hit O twice, that'll select the shapes tool. We can go for rectangle and then opt to fill the rectangle so that after we right click down here to select a secondary color, it will give us a bit of shading and make the box look good. This is sort of up to you what you want it to look like if you want to give some color to this kind of thing. A little bit more fun. All right, next we're going to go back to the line tool, and now we can hit the / to turn it into an arrowhead, and maybe increase the brush width to like a 4 and choose some different color for this and put on, whoops, I selected the secondary there. So we want to go to up here and then left click to put the primary rather than the secondary. Right click seems like it can select the secondary, but then once you've done that, it can get messed up if you go and select in the main color palette too. All right, so you can also just click on the square that you want to select in order to change the color more directly there. All right, anyway, we're gonna go to, let's say, red, and then draw some arrows here. So we can call this one what did we call it? F, the force that's applied on this block. Hit T to be typing, and then we'll change the font. Actually, let's type first. F, and now we'll make this look good. How? By increasing the font size and changing the font to Times, which is the same one we're using for math symbols over here, and then change this to italic to make it look exactly like it was in the notes. If you were using a different font for math in the notes, then you would use a different then you might want to style by making the font appropriate over here. Okay, making that whatever one you had. Next, what else are we going to have on this? We're going to have a friction force going backwards here, which is, maybe we'll call it FF. And we're going to have a normal force from the surface to stop this block from falling through that. And we're going to have some weight of this block, capital W, which is the effect of gravity. Okay, so there is a free body diagram. Another thing we can do is label the x-axis. So it starts at 0. Maybe we'll go with something like this. Turn off the arrowhead. We can also use the dot to make kind of a dashed line, and then say, this is going to be our axis, like the starting point for x equals 0. Okay, so we don't want the 0 to be italic. So if we really want to be fancy here, then we have to kind of start another one and say not italic, and then type the 0. And then we can show that this direction to the right is the direction of increasing x. So I'm holding shift by the way, to make it snap. If I don't hold shift, it will go to any spot, but holding shift will make it snap to kind of like certain angles. It looks like 0 degrees. Then we've got 1, 2, 3, 4, 5. 1, 2, 3. 3 is going to be 45 degrees there. And then you've got fractions of 45 degrees. So 1, 2, 3, 4, 5, 6, all the way around for the division, kind of 6 steps up to there. So what would that be? If you've got, so if this is pi by 2, it goes in steps of pi by 12 then. Yeah. All right, so let's take this thing and change it back to solid by hitting dot enough times, and then hit / until we get an arrowhead there again. And we'll put a little label there that this is X. This is the increasing X direction is what that means. Okay, there we go. Now we'll hit S to get our selection tool, and we can copy all of that and put it into the notes to get our free body diagram there. So the block starts at X equals 0. And even though the block is not at X equals 0, that just means that we're not drawing it at exactly the start time. Next part, use Newton's second law to derive the block's differential equation of motion for the initial part of the motion where the block is moving in the positive X direction. So assume that the block is moving to the right so that friction is directed to the left. Okay, yeah. So Newton's second law is that force is equal to mass times acceleration. But technically, we should be dealing with this in vector form. And we can say that the acceleration is the second time derivative, that's the double dot format, of the vector position, where r is equal to xy, the position of the block. Now in this situation, nothing is happening in y. The block can't move in y because there's no force causing it to move up, except for the normal force, but that only is going to stop it from moving down. It can't cause it to lift up off of the ground there. So the block can't move in y. Therefore, the y position is always equal to 0, right? And that means, we can use our therefore symbol as well, that y double dot is equal to 0. So r double dot is equal to x double dot and 0, but this is equal to the force divided by the mass. And the force we can get by looking at this free body diagram. So net force in X would be equal to this forward F applied there minus FF, and the net force in Y is the normal force minus the weight. So by comparing the left-hand side and right-hand side of this, we've got an equation for the for what the normal force has to be. It's not always going to be like this. Like if this was on a ramp, then you wouldn't have all of the weight directly counteracting the normal force. But in this situation, we do. So 0 equals n minus w, then leads us to n is equal to w. And once we've got that, we can apply the fact that the friction force is equal to mu k times n to say that it's equal to mu k times w. We could substitute that in, and then write that x double dot is equal to 1 over m times f minus ff, where we've now solved for everything. So we've solved for the friction force, which we could sub into there. We've solved for the normal force, which we could then sub into there. And I guess we could also say what W is. W is equal to mass times little g. Okay, so let's check. Used Newton's second law. We did that, F equals ma. To derive, come up with a formula for the block's differential equation of motion for the initial part where the block is moving in the positive x direction. So we did that. What is it that causes that makes this for the block moving in the positive x direction? Well, the fact that the friction force is directed to the left. If we had the block moving in the negative x direction, moving left, then the friction force would have been directed to the right. All right, part C, use Maple to solve the block's differential equation of motion and determine when and where it first comes to rest. So the time and the x coordinate when it first has a velocity of 0. Plot the position, velocity, and acceleration on the same graph and output the time corresponding to the location of when the block first stops moving. Okay, hint, because we're assuming friction points left, this graph will only be correct while the block moves right, so don't draw it too far past where the block first comes to rest. I'll revisit this and explain this after we've kind of done this part. Okay, so Maple. Gonna restart, and then we're going to type in the stuff that we know here as variables. Maybe we'll hold off on that and see if we can write out these equations first and just view them before the variables are assigned. Okay, so we've got our dE, which is going to be 1 over, the second derivative of x. We could write this in a couple of different ways. Let's just use the diff notation because it's a little bit more straightforward. Diff of x at t with respect to t twice is equal to 1 over m times f minus ff. Okay, so there's our differential equation. Wow, all right, that's not going to be so bad. We just need to assign the things that we figured out earlier. So big F, let's actually start right at the start here, I guess. G is equal to 9.81. M is 5. The x equals 0 is the initial x position. So we could write that as our ICs. The initial conditions would be x at 0 is 0, and it starts from rest. So that tells you that the rate of change of x, first derivative, d, you could say 1, but it's implied, of x at 0 is also 0. Okay, so there's our initial conditions. Let's see if that looks okay. Looks okay. What's next? We've got what f is. 30 times cos squared, cos of t squared, minus 20 times t times e to the negative t. Doesn't really matter how complicated looking this is. We're likely going to be able to solve it without too much difficulty if we're doing things numerically anyway. And we've got a coefficient of friction. Mu k is 0.3. Then we can type in the things that we figured out down here. So W is equal to m times g. N is equal to W. FF is mu k times n. And I think that is it. Okay, so now once we've got all of these things assigned, we're going to have things substituted in down here. As you can see, the F has already been subbed in, but we don't know what FF is. So now we can back substitute in the other things we calculated. So it looks like FF is completely known. Does that make sense? Well, it was mu k times n, and n is fixed, doesn't depend on the motion. Mu k doesn't depend on the motion, so that seems reasonable that it should be a number. Is this about the right size for this number? Let's see, we've got 5 times about 10 is like 50 times 0.3 is, let's see, right, we divide back out the mass, so divided by 5. So 5 divided by 5 basically means that we've just ended up with g times 0.3. This is something we could also have checked by going and doing this substitution ourselves here. So f over m minus ff over m, and let's also substitute in what ff is. So ff is mu k n, and n is mg. So f over m minus mu kg. Yeah, you could have simplified this here and then substituted in at this step, but we would get the same answer. Mu k times g is going to be that same value that we have there at the end. Okay. So now that the differential equation is typed out in this format, we can solve it using dsolve. We give it the differential equation and the initial conditions, and that should, I've made this mistake a couple times before. The initial conditions are not actually supposed to be in a list. They're just supposed to be a set of comma separated values. So we could have either gotten rid of these brackets and then it should work. Yeah. Or we could put the brackets back in and then say open the ICs if you really feel like making the initial conditions laid out in a list. Either way, you're going to get this as just separate comma separated things. This version of Maple that I'm using anyway can't deal with them as another list within a list here for this. So what was it about the error message that was telling us that? Because that can be kind of good to dive into as well. It said in dsolve with initial conditions, we had an invalid input. The left-hand side argument received this thing, and we recognize this, hey, that's the thing we had as our ICs, so there's some problem with the ICs. And this is not valid for LHS, so that means it's looking for an equation for this, but we gave it a list of equations, so perhaps there's something wrong with the fact that it was interpreting this whole thing as one argument, and it kind of wanted one equation, which means it wanted these as separate comma separated things like second and third arguments. If it was a third order differential equation, it would just need 3 separate inputs here rather than a single input, which is a list of ICs. So that was the hint from this error message. Get rid of the list either by using open or by just making ICs assigned this kind of set of comma separated things without being officially a list, and it'll work. So the next step is to have a look at this solution and see if it's meaningful. We have first to assign this to something. So let's just call this x. X is the right-hand side of the previous thing, and that'll make x assigned to everything that was to the right of this equal sign. So now we can see what x is just as a check. Yeah, x is everything that's over there. And now we're in a position to plot that. But before this gets too busy on the screen, maybe we'll see if we can fix that up a bit by either going to like a smaller zoom. I think this is maybe getting too small in the font size. I'll be interested in feedback on that. It depends on the monitors people are looking at. If you're watching this on your phone, I could see this font being pretty small, so we won't go too much smaller than that. Instead, let's suppress the output for these things that we don't need output for. We can put a lot of things on the same line as well, if we don't need them to be echoed back at us. Yeah, same with the DE. And the dsolve command, we don't need any of that output anymore. Great. So now we've simplified stuff, and we can just get what x is at the end here. I wonder, maybe it'd be good to see it like this, because then we'll see the x equals. All right, great. Now we can plot that. Let's have a look at what x looks like from t is equal to 0 to, I don't know, 5. Okay, so we have moved up and then started to go back and backwards for a long distance. Now, you might remember that this setup is only valid as long as the block is moving to the right, moving in the positive x direction. So that means this is not going to work past a little bit past 1. So let's go to, so we're going to want to change this to something like 1.5, 1.2. We'll figure out what it is. But again, this part of it is not a real solution for this, because as soon as the block starts moving in the negative x direction, so starts decreasing its x position and moving backwards like this, the friction force should change to point in the other direction. But we didn't tell the thing to do that. We just said that the equation was x acceleration is this minus the friction force, which makes the friction force always point in the negative direction, even if the block is moving in that direction. So this is only valid as long as the block has a positive velocity for x. Okay, so let's change the range to something like 1.5 for now. And you see that's too much. You could zoom in and try and figure out exactly where this spot is, but we can do better. We can define the velocity as the derivative of x with respect to time, and then look at that instead, or maybe even in addition. The velocity has different units than the position, so it's a little bit funny to plot them both on the same graph, but as long as you keep in mind that the scale is different. So for position, for the red graph here, we are in meters, and for the green graph, we're in meters per second. Now, this is getting to 0 at exactly that spot. So we can kind of zoom in on that again with the plot to look for that position, but we would do, we'd have a better job at finding that if instead we used fsolve. Fsolve is a command in Maple that lets you find out where something is equal to 0 and specify a range. The velocity is also equal to 0 at the start, so if we just say fsolve v, we'll find that. Yeah, that's telling us, all right, well, when time is equal to 0, velocity is 0. That's not really what we wanted, so let's give it a range. T equals 1 to 1.2 should be enough to zero in on that. Put the bracket back that I just accidentally deleted, and 1.122. Okay, so it looks like at t is equal to this. Let's assign that. T stop, fsolve that. So t stop will be equal to 1.122. At that time, we should have a velocity of 0 and a maximum position. So let's check. Plotting until t stop, looks like we hit exactly the spot where it stops. And we can find out what that final position is by reporting it. So x stop is equal to substitute, subs, t equals t stop into x. Now this is the direct substitution, but we actually want a simplified version of that. So let's also say, evaluate this as a floating point, evalf. So it looks like it stops at about 0.7, which seems right from this graph. We can kind of, so if you put your cursor on the plot somewhere, it will also show you what the output was up here in this little box. Or do fancier, newer things in whatever futuristic version of Maple you're using. So that's another way to read it. You can just kind of read it off the plot directly by clicking on things. The last part is to plot also the acceleration. We've outputted the time and location when it comes to rest. So we just need to add acceleration to this graph. And we can do that by defining a new variable. A is equal to the derivative of velocity with respect to time. Okay, so here is the position, velocity, and then the acceleration all on this same graph. The acceleration is a larger, is larger in magnitude than the other graphs. So we might want to actually plot acceleration scaled a little bit. Maybe we'll plot acceleration over 10, just so it's not dominating the other ones. And now we could put in a legend as well. To remember what the syntax is for that, you can go to the help menu by hitting F1 and then searching for legend and looking down at the bottom. They usually have code samples of what the syntax is. So here we go, plot, and then as one of the arguments to plot, give it something like legend is, and then use strings inside a list to be associated with each of the things that you plotted. Okay, so that means on this plot, we would want to go legend equals the first one was x, and we'll say that that's in meters. And then we'll go v in meters per second. And then we'll go a in, let's see, this is in, since we divided it by 10, something like 10 meters per second squared, right? Let's see, we can actually use Shift Enter here to break this command over multiple lines and make it easier to read. So the acceleration is in decameters per second squared. By consulting the chart in the notes, you can see that decameters metric prefix is actually DA. So to be technically correct here, we could go DAM per second squared, decameters per second squared. But if that's a little bit obscure and confusing, you could just say in 10 meters per second squared to be a little bit more clear. Up to you. So this shows you that it's in tens of meters per second squared. And that should get across this idea that we're looking for here. Once you've got the whole thing laid out in code, you can copy it, Control C, and then go over to here and say code and Maple output and paste that into there, and it should work decently well. I find in newer versions of Maple it annoyingly inserts a bunch of these greater than symbols in the lines here when you paste it in. So if you have a solution around that, then then let people know in the chat, because that's a problem to get around. This is an older thing that was available in older Maples, is classic worksheet Maple. So in the version I'm using, they have this even older style where you don't have to use the 2D style of programming, and it makes it a lot more like coding and solving the system that way. All right, now question, does this seem reasonable? The block starts moving and then it comes to a stop because the acceleration is positive, and then the acceleration is negative after the block has gotten up to a certain amount of speed. So what is it that's causing the block to have this decreasing acceleration and then negative acceleration and then come to a stop there? Well, the friction force is constant the whole time, so it must be this interesting force that we're applying to the block externally. We can explore that by also, let's say, modifying this plot to plot instead. I wonder if I can do this. This is a soft line break. Does the comment continue to apply to this too? No. So if you're going to use this one line comment syntax, you've got to put it, get rid of the soft line break. Okay, so let's add into this plot a plot of F. We'll also add it into the legend for completeness. So this is going to be the force in, so far, newtons. That might be too large to compare to the other ones. Yeah, okay. So let's maybe have the force divided by 30 to put it on the same scale. Okay, so force another way to put this is force over 30 in newtons. So rather than saying the acceleration in tens of meters per second, we could have just said that this is acceleration over 10 in still meters per second squared, I should say, not seconds. This also gets across what it is that you're plotting there. Okay, so force over 30 newtons. Looking at this, you see the force starts up high and then it goes down, but the point where the acceleration goes to negative is not the same as the point where the force goes below zero. Why is that? Well, because we're competing with the friction force. So probably this point is where the force is going to be the same magnitude as the friction force. Let's plot the friction force too. Also divided by 30 to put it on the same scale. ff over 30 in newtons. Close that string, and then we should have it. Aha. So as expected, this spot here, where the acceleration becomes negative, is when the externally applied force is no longer more powerful than the kinetic friction. And that explains why the block has reached its max velocity at that point and then starts to slow down afterwards when the externally applied force gets smaller and smaller and eventually even negative. Next part is going to be to repeat this whole thing, but in FlexPDE instead. So let's give that a shot. We're going to take FlexPDE. We could build off of a previous one, but let's just make a whole new file. Let's call it 2019, so practice problem 2020 point 1. Yeah, why not? Okay, so here's our new FlexPDE file. We can optionally give it a title, maybe flat block, and we're going to need to set up some variables here. So what do we need? We need a position. We can't use X because that's already reserved for the coordinates in this grid that we're solving. So we've got to use something different. So I usually use XD for X displacement, and we need to give it a threshold because we're going to be doing a time-dependent problem here. We're also going to need the derivative of this for the velocity, so velocity in X. Now under select, we can optionally say ngrid is equal to 1 to make it faster, but that's not actually necessary. It'll just save some time later in how long this takes to run. So definitions. Here we can set up the variables. M is equal to 5, G is 9.81. I suggest that you don't just look at your Maple code and copy over the variables you typed there, because this way you can use it as a source of error checking. So go all the way back to the source and start typing in your variables here. Really use it as a solution that's independent of the way that you implemented it in Maple to check, to have a way to check for more sources of error. Double check your work a bit more. Okay, so now we'll put in the force. Force is equal to 30 times cos of t all squared minus 20 times t times e to the negative t. Then mu k is 0.3. Notice that compared to Maple, we don't need to use colon equals to assign things. It's just equals in FlexPDE. Okay, next up, we could similarly assign all of these intermediate variables, or just go right to the final thing here and say that the acceleration in x is equal to f over m minus mu k times g. Okay, we don't need initial values because they happen to all be 0, but if you wanted to assign them anyway, you could say xt is equal to 0, vx is equal to 0. Again, this is the default, so this whole section doesn't need to be there. All right, for equations, we're going to need 2 of them. The equation for xd will be that its time derivative is equal to vx. The equation for vx is that its time derivative is equal to the x acceleration. All right, we don't need to mess with the boundaries because none of this depends on the location within the block. And we'll set a time. The end time has to be at least as large as where this would have stopped before. So let's pretend that we don't know where it's going to stop. And we'll say time 0 to 5. And now what we can do is implement a halt condition. So we'll say stop if Vx is less than 0. Now we'll need a plot at the end for t equals 0 to end time over to end time, and maybe we'll put in some steps. T equals 0 by end time over 20 to end time. And now the actual plot history of xd, and I always forget the syntax for this. So let's just guess and then see if we get errors. Oh, that's good. We got it. All right, so history xd at 0, 0. We can put in other things. vd and ax over 10. Oh, it was vx. Yeah, that's it. All right, so that looks pretty good. This plot probably is familiar from what we saw in Maple. Notice that it went a little bit further than it did in Maple because we're not getting an exact solution for this and then substituting and then finding out where it stops. We're doing time steps forward and stopping as soon as the velocity ends up being negative from our numeric solution. Despite all the approximations that go into making this happen with the finite difference method and stepping forward and all that, we end up with a very similar solution, which we can then report. Summary, report XD. That will not work. It should be report val of XD at location 0, 0 within the grid. Yeah, so here's the final position. And we can say if something doesn't depend on a position within the grid like time, we can just say report T to report the stop time, the time that this actually stopped. Okay, so that shows how you would solve this using Maple and using FlexPDE. To give the output of this so that somebody else can reproduce it, it's kind if you either submit your FlexPDE code, but then to make it easier for someone else to view the solution, you can paste the direct code into a file here to make it quick for you to come back to this later. And it's good to show some kind of an output from this. So you can take a screenshot of this set of plots and the summary that you'd like to report and put it in here as well. Okay, so that would be the solution if you were going to be presenting this with a video like I'm doing here. So that concludes the discussion. We talked about things, we analyzed it, we looked at some more advanced things in Maple, but if you're only going to be handing in this file, this really doesn't cut it, right? Like if you look at what we actually wrote down, we just did this, no explanation. There's this, there's a lot of things that I said that weren't written here. There's the code without much of an explanation of where we got it or how we put stuff in. There's the raw code in FlexPDE, and then this set of plots here, but no analysis, no looking back. The text here that's actually written is lacking in a lot of ways. So let's see if we can improve it and include some of the things that we talked about as discussion points here. So first, let's put in a heading, solution 2020 video, and I'll put a link right underneath here. And then also this discussion. So let's make the free body diagram. Free body diagram, okay, is as follows. Perhaps, or maybe just free body diagram, either way. And this says, maybe we'll put in a note, at least as long as the block is moving in the positive x direction. Otherwise, the friction force, FF, would be directed to the right in order to oppose motion. Okay, now solving it, so maybe we'll put in a label because that was part A. B. Maybe Newton's second law says this, where R is equal to that, and maybe we can include another thing that explains what F is. The net force on the block is that, where R is the position of the block. Okay, the block can't move in Y, therefore this. So let's see, the rest of this seems like it makes sense, and we've got that as the acceleration. Maybe a concluding statement. So the acceleration of the block is this. X double dot equals F over M minus mu kg, as long as the block is moving to the right. Okay, C. Implement this in Maple as follows, and we can plot the solution here Yeah. Okay, so this shows that the block first comes to rest at position x stop equals 0.7 meters to the right, after time t stop equals 1.1 seconds. Maybe it's hard to know how many significant figures we can actually put into this. Depends on how many significant figures we had at the start of this. So since we started with information that mu k is 0.3 and it's 5 kilograms, we don't have more accuracy than that. It's hard to say, justify too many significant figures for t-stop. But since it's changing quickly in time, using 1.1 might not be accurate enough. So we'll say 1.12 seconds to kind of summarize that. This also is the, well, I don't know, we didn't quite get that threshold with FlexPDE, so maybe 1.12 is a little bit too precise, but it I think we're okay for now. So this comes to a stop after t-stop is this. Now we can analyze the reason for this. The reason is that the acceleration became negative after about 0.5, maybe let's say a bit after 0.5 seconds. Shortly after 0.5 seconds. Further analysis shows that this is because the driving force F is decreasing in time, and after, let's say, and shortly after 0.5 seconds, it is no longer strong enough to overcome the friction. Now we can include that other plot that we did with Maple. So for that one, we can copy just the plot and the code that we used to come up with it. Right, so this is pretty good. We've included more analysis now and the summary of that. Okay, next part, which is part D, FlexPDE solution. Maybe just comment that it proceeds similarly to the Maple one, where we've included the definitions as before, put everything in terms of acceleration. We can put in comments. Acceleration. It's probably better to put this in Flex and copy it over, so it'll be more clean when you also submit your Flex code. Position, velocity, acceleration. Yeah, initial values. And I don't think there's anything else to really explain. Everything else uses the same variable names as we did in Maple. So as long as somebody goes and reads this right after they've read the Maple stuff, it should work. Okay. Oh, I didn't say earlier, the way that I changed this to Courier font so quickly was with a macro. So I made a macro years ago that turns it into Courier with Control-Shift-4. You could do that yourself with the macro recorder in Word if you liked. The Courier is kind of useful for typing in code, and because it's a mono-spaced font, so this makes it clear to see where the spaces and all that are. Now to change the size, that's not with a custom macro. That's just in Word, select things, and then hit Control control less than, control greater than. So that's control shift, comma, and period. Right, okay. So that gets across the flex solution, and then say this matches with what we observed in Maple. I guess matches, not matches with, matches what we observed in Maple. The block stops at about 1.1 seconds. Let's say after about 1.1 seconds at location 0.7 meters to the right of its start position. So now that we've saved the code and everything, and we could easily come back to this, it might be time to create an extension to this. This is not asked in the main problem here, but it is asked in the separate extension problem. So we can explore this. Modify either your Maple or Flex code to account for the true direction of friction and plot the actual position, velocity, and acceleration for t from 0 to 10. Yeah, so let's put this over here in the new solution file as well and say extension, explore this for t is, maybe we'll say, we can also explore this for t is greater than, maybe for t equals 0 to 10 seconds, use the Maple syntax for a range there, by modifying the friction function to point in opposite the direction of motion. The way to do that is much easier in Flex than in Maple. What we would need is that this minus actually is just negative the current velocity direction, right? So we'll say that this is maybe the friction force. Well, actually, I guess that's the friction acceleration. The friction force would be mu k times m times g, and then we would say friction force over m. Yeah, so this is the friction force magnitude, but it's this, the direction of this would be modified if the thing is moving to the left rather than to the right. So we can do that. First of all, let's just check that we haven't changed anything yet. Yeah, so that's the same as before. We can do that by, actually, let's just get rid of the halt condition for now. Comment this out and go to 5, see what it would look like. So if we don't correct the fact that it should be switching directions partway through, then it's going to keep going down there because the acceleration just is kind of cyclical with this force, and the friction is always pointing in the negative direction, so we just have something that's constantly moving downward. So let's fix that by modifying this based on the velocity direction. One way to do this is to say Vx divided by the absolute value of Vx, but this won't quite work. So this is something which is which has a magnitude of 1 and points in the direction of the velocity, right? So if velocity is positive, let's say it's positive 3, then we've got 3 divided by 3. Absolute value doesn't change that. But if it's negative 3, then we're going to have negative 3 divided by 3, so negative 1 instead of 1. So let's see what happens. If we run this, we get a divide by 0 error because right at the start, the velocity is equal to 0. Now, the computer doesn't know how to interpret this because it's either plus or minus and it has this big discontinuity there. One way to get around this is to say, well, okay, that's fine from a math perspective. I could see why this would be a problem. But from a physics perspective, we know it's initially going to be going to the right because that's the direction of the force. And we don't really care about the friction if it's moving so slowly that the velocity is basically 0. So one way to fix that is instead of dividing by the absolute value of Vx, divide by that plus some really small number. So let's say 1e minus 5. This doesn't make any difference if the velocity is like like 1 meter per second or even 1 centimeter per second. It matters very little then. It's like a 1 in 1,000 part change to this. But it makes a huge difference for this computer program being able to deal with it when the velocity is very close to 0. So now it solves no problem. We've got this position that increases and increases more with time. You can see what happens now. The friction is enough to overcome it and totally stop the motion right around here when the applied force is not very large. We can make another plot to compare those things. History of, let's say, F and FF. And now we're going to plot the friction force and the external driving force here. So the friction force is its maximum value as long as the block is moving, and then it stops. And then it's, what is the friction force now? Then look at this, it matches when the block is not moving. This part here where the block was not moving, the friction force is just whatever it needs to be to overcome the driving force. Isn't that great? It kind of mirrored and did exactly what you would hope static friction to do, opposing the driving force, because we've added negative this, right? So we're subtracting the two together. So we ended up with a friction model that opposes this driving force and cancels out exactly what it was doing until the driving force is stronger than friction can be, and then it just is as strong as it needs to be while the thing is moving. Okay, so that's pretty fun. Let's include, I guess we need it up to 10 seconds. Yeah, so let's change this to 10 and include this set of plots as well. So now we can see what this would be. Oh, I cut off the legend a bit. Let's try another screenshot. In Windows, by the way, the shortcut for the screenshot is Window key Shift S by default. Okay, so there's that. And double click to make that small again, then double click on this to maximize that one. We've got the force and the friction force. And let's put in our discussion. So now let's say we can modify this. We can modify this in FlexPDE by changing the friction force to, let's say first, writing the acceleration to include the friction force directly. Show that. And changing the friction force to always oppose motion. And let's see, we can show this part at the end. Using the term Vx over the absolute value of Vx plus 1e minus 5 creates a, let's see, will cause, let's say, cause FF to be positive when Vx is greater than 0, negative when Vx is less than 0, and not and not have a discontinuity when Vx is close to 0. Right, so let's just check. The denominator is always positive, so this is true about the sign. It's going to have the same sign as Vx, and it's not going to explode because of the 1e minus 5 thing. This produces the following position, velocity, I guess we do need commas, and acceleration plot. Notice also that the force is the friction force. I guess we should comment here. The block stops and starts, but never actually moves backwards. Notice also that the friction force is only active, maybe maximized, when the block is actually moving. Otherwise, it ends up being just large enough to cancel the motion, cancel the externally applied force. And make acceleration 0. Yeah. Okay. So this is pretty much it. We've included explanation now around this extension problem. We can close it off by including the final code. And yeah, so to recap, we took this problem, we dealt with it by first drawing a free body diagram. That's usually the way that you want to start off these things, so you can think through the Newton's second law and the force method of generating the differential equations, worked it into a differential equation on position that we can solve, and then implemented it in Maple using dsolve to get the solution to this, explored around, looked at it, and reasoned why it should be looking the way that it does, with the block moving up and then coming to a stop there. Then repeated it in FlexPDE and verified that our solution matched with what we got in Maple. And finally came up with an even more challenging problem of dealing with this when it is moving backwards. And for this one, it would be very difficult to deal with it in Maple, but dealing with it in FlexPDE showed not much trouble, because it doesn't care if the block has a complicated differential equation that sort of depends on what way it's moving. Maple would be concerned by this because it makes it a nonlinear differential equation. Okay, so that's it. Thanks for watching. I'll see you next time.